Hello. 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 Yes. Hi. This is a live session for the graph theory course. Hello. Yes. Hi. This is a live session for the graph theory course. Hello. Yes. Hi. This is a live session for the graph theory course. Hello. Yes. Hi. This is a live session for the graph theory course. Yes. This is live session for graph theory course. Hello. Yeah, so hello. Okay. Yes. Right. Where do you? I don't see any question anywhere. Um, Start discussing about the about something just, or I don't see the questions. That's the problem. Let's make sure. Yeah, so I got that questions now. Okay. Okay. Okay, so I can just start answering any questions. It is listed here, right? Oh. Okay, so I'll talk about. I picked this question first. This one is there is a question: what are the projects of graph theory that one can do on completion of this course, both research and industry? This is by Karamjit Singh. So, well, I mean, there are different projects that you can do. Some of them are at research level, and some of them are at project level. So the project level that one can do as a master thesis or master project is that so for example, you have seen the graph theory. In graph theory, you have seen the matching in bipartite graph. So we know how to find maximum matching in bipartite graph, and but we don't know how to find maximum matching in general graph. Like you take any arbitrary graph and try to find the maximum matching in that graph. So that part we have not covered. So this is, one can explore, which is slightly difficult compared to the augmenting path algorithm that we have learned for bipartite graph. So the one direction could be like, you just learn advanced topics in graph theory. So one example is that by matching in the general graph, and some special area like say one can study also like what is perfect graph, and all these things. And at the end of this course, you will see that we talk about coloring of graph, and we talk about four color theorem, for example, without proof, because proving this theorem is not so easy. So one can consider also to know the proof of four color theorem. So these are the things you can, and the course that we offer in NPTEL is a basic level course, but you can learn the special topics. And this is one. The other way is that you also asked what is the application of this course in industry, for example. There are many applications of this. I considered the example of say bipartite matching again. So of course, matching, if we consider the example of boys and girls, one side is boy, one side is girl, and try to find a matching, but it can be like one side is employees of industry, and the other side is the assignments or the jobs that are available, and you can sort of find you can find a matching between the employee and the assignments that is available for assignments that are available in that industry. So so there are many applications that one can think of graph theory. I just gave one small example. Okay, so with this one, I'll stop answering these questions that what are the projects of graph theory that one can do on completion of this course, both research and industry. Okay, so research level, there are, you can think of algorithms. See, without algorithms course, the graph theory is not complete. So some basic graph theoretic results, but you should also do the algorithm course. And once you are done with the algorithm course, sort of your knowledge in graph theory is complete in some sense. It depends on what is the details you study in the algorithm course. And then once you're in the algorithm, there are several research problems, graph theoretic research problems which can be solved using algorithm. You can think of, say, something like NP complete problem, and which are graph theoretic NP complete problems. And You know, the graph theory NP complete problem nowadays, the area that one considered is that how to deal with NP complete problems. So NP complete problems are the problem that there is no known polynomial time solution for any such NP complete problem, and then we need some practical way of deal with NP complete problems. So one is that approximation algorithm. You don't find the optimal solution for the problem in polynomial time that is not known for any NP complete problem, but you can think of approximation algorithm, which is like you give a near optimal solution, and the near optimal solution you are giving in polynomial time. So this is one way of dealing with NP complete problem. And there is new area called parameterized algorithm, which I also started working on. It's a research level. This is another way of dealing with NP complete problem, which is slightly advanced. So I'll not talk about this one at this moment. Okay, so this is, I think I'm done with answering this question by Bhaskar. Yes. Now, there are, let me move to another question, like, this is a question by, okay, so the question is, sir, can you please explain me about the augmenting path related to matching, and I'm not getting the assignment for question number 3. Okay. So here, I think the major problem with augmenting path that you are facing is that you always think that, okay, what is augmenting path? First of all, augmenting path is an alternating path, which starts at an unmatched vertex and ends at an unmatched vertex. And the edges will be alternating, like unmatched edge and then matched edge and then unmatched edge. So the major difficulty that we face is that we always think that augmenting path must contain a matched edge, which is not required. Suppose you know, the augmenting path you are considering is of length 1. Just that means it has only one edge, and that edge must be an unmatched edge, and the two endpoints are unmatched vertices. So this is also an augmenting path of length 1. So augmenting path of length 1 is just consisting of just one edge, and that edge must be an unmatched edge, and both the endpoints of this unmatched edge must be unmatched vertices also. So that's also an augmenting path. And the next possibility is that you can have an augmenting path of length 3, for example. Then the sequence will be like that, like this. Like the first edge is a unmatched edge, and the second edge is a matched edge, and the third edge is a unmatched edge, and the starting point and the end point, that means the starting vertex and the end vertex, both are unmatched vertices. So this is also an augmenting path, and this is an augmenting path of length 3. So I think the only misunderstanding that you have at this moment is that you don't think about an augmenting path of length 1, which is just an unmatched edge and both the endpoints are unmatched. vertices. And then you can see in the assignment 4, the question that you are given, there is an augmenting path, which is of length 1, so that you can, I think now the solution is also there in the portal. You can check that, and I hope that after this thing, that the augmenting path can be also of length 1. I hope that you will be able to understand the question, and you will be able to answer the question there. Okay. Of course, I mean, this is a nice question, because there are difficulty with many students. And next, I move to another question maybe. Okay, so I move to another question by Srinivas, which is he's a faculty. So your question is, matching topic was not clear. Okay, and the assignments are not related to video NPTEL. Okay, I don't know whether this is true. Okay, so you could not understand matching topic very well. So that's the comment here. Okay. Okay, so let me just tell a few things about matching, if this helps you. Like, so a matching in any graph, whether it is a bipartite graph or general graph, it does not matter. So a matching is a collection of disjoint edges. Like, all the edges that you consider in the matching, they must be disjoint. There is no common endpoint. And what we try to do is that, given a graph, we try to find maximum matching. So it's a maximization problem. And we considered the simple case because matching problem is difficult in general. So we consider the problem of finding maximum matching in bipartite graph. So we consider a special graph, and this is easier. It is easier to find maximum matching in bipartite graph compared to matching in general graph. That's why we consider finding maximum matching in bipartite graph, and we talked about augmenting path algorithm. So what you do in the augmenting, so we talked about what is augmenting path in the previous question. So augmenting path is a alternating path, which the edges alternate between matched and unmatched edges, and the first vertex is a unmatched vertex, and the last vertex is also an unmatched vertex. So what you do is that you start with a say empty matching initially, and then you try to find an augmenting path in the bipartite graph. So what will be an augmenting path at the very beginning is that just an unmatched edge. This is an augmenting path, right? You just pick any edge, and since you're picking one edge at this moment, this is anyway disjoint from your collection of edges which are in the matching M. So at this moment, you just pick one edge, and that is the matched edge for you at the very first iteration. And then you try to improve the matching at every iteration. What you do is that then the concept of augmenting path, you apply the concept of augmenting path, that at every iteration you try to find another augmenting path with respect to the given matching. Now this is the problem there. You might find an augmenting path involving this matching matched edge that you have considered already in the matching, but it is not necessary. You can find an augmenting path of length 1, for example, which is just an unmatched edge, and both the endpoints are unmatched. It's not necessary that you have to include the matched edge that you have in your matching, in the current matching, in your augmenting path. It's not necessary. But if you can include, that is also fine. You can find a augmenting path of length 3 involving your, once it is a augmenting path of length 3, there must be one matched edge and two unmatched edges. So you can so you have to include the matched edge, that the only matched edge that you have in your current matching to get augmenting path of length 3. So this is probably the major difficulty that many of you faced, that you always think that, okay, I have a matched edge, so I have to include this matched edge in my augmenting path. Not necessarily. Without including any matched edge, if you can find an augmenting path of length 1, that means it's just an unmatched edge, and with both the endpoints are unmatched vertices, you are fine. That's also an augmenting path with respect to the current matching. And then you take the symmetric difference of the current matching and the path that you have. You probably refer the lecture to know what is a symmetric difference, and you see that every time you improve the size of the matching by 1. So this is how at every iteration we increase the size of the matching by 1 if there exists an augmenting path, and we stop when with respect to the current matching there is no augmenting path. That is the stopping criteria. So okay, so I think now probably it will be slightly easy for you to just go back to the lecture and see whether you understand the concept of or the algorithm to find the maximum matching in bipartite graph, which is the simple case that we considered in the lecture. With this, I'll stop answering this question. I'll just request you to just see the lecture, the videos once more, and you can write to me if you still have difficulty. Okay, now I just move to other questions. So the question is, can you please tell me about exam paper patterns? The questions were easy or difficult? Okay. Okay. So exam paper pattern. Yeah, pattern I can tell you. Okay, I think I can answer both the parts of these questions. So the first part is that what is the pattern of the question paper? So the pattern of the question paper is MCQ, multiple choice questions, and I believe there are 3 sections. The first section, section 1, it will be mostly easy questions, and you are sort of basic, whether you understood the definitions, and if you understand the definitions and remember the definitions, you will be able to solve section 1 easily. Okay, And then so in the first section there will be 20 questions about, and then section 2, each question is of like 2 marks probably, and they're slightly difficult compared to the first section, but not that difficult also. I mean, if you understand the course, it should not be difficult. And let me just complete. In the third section, you have a few questions there of marks like 3 and 4, and still here you can see maybe some difficult questions which are not direct, but they are all solvable problems. And you can also, if you have done the assignments carefully, you can see that similar pattern questions are there in the exam. I think that's enough hints about the question paper pattern and all. And your second question is, sir, tell me once again about stable matching. Okay. I don't know how much I can talk about this one, but so what is the matching problem is, so matching in a graph is the collection of disjoint edges. So when you talk about bipartite graph, one side is boy and the other side is girls, and so matching is a one-to-one correspondence. You can match one boy with one girl. You can't match one boy with two girls or one girl with two boys. So that's the whole idea of matching. So this is matching is a one-to-one correspondence between boy and girls. It's easy to remember. Now, in usual matching, if you remember the bipartite graph there, from one vertex which corresponds to a boy, it is adjacent to, say, B1 is adjacent to G, G1, G2, G3. That means boy 1 prefers girl 1, girl 2, and girl 3. So you can match boy 1 with any of these girls. So this is the setup in the usual matching problem. But in the stable matching problem, it is slightly different. So every boy, not only, so in the previous setup, if boy 1 is adjacent to girl 1, 2, 3, so they are equally preferred by boy 1. But in the stable matching situation, it is slightly different, that each boy has to give a strict preference list. Suppose there are 4 boys and 4 girls. So each boy has to give a strict preference list, and similarly each girl will give a strict preference list. And then we talked about, so it's becoming almost like a complete bipartite graph, but there are strict ordering. So here we talked about the stability of the matching. Stable matching. Stable matching is a matching where there is no blocking pair. So what is blocking pair? Blocking pair with respect to a matching. So a pair AB is said to be a blocking pair with respect to a matching M. In the sense that, see, this blocking pair AB is not part of the matching, it is outside. So A is not matched with B. And when they will be blocking, if A prefers B more compared to its matched partner in the matching, and similarly, and it's not or, that and B also prefers A more compared to its matched partner in the matching. That means A and B prefers each other more compared to their matched partner. Then this is a blocking pair. And matching which is not containing any blocking pair is called a stable matching. And we saw how to find a stable matching in the set of once given an instance, how do you find the stable matching using Gale-Shapley algorithm? So we talked about the man-oriented stable matching, woman-oriented stable matching, all these things. So I don't know how much you expect from me about talking about stable matching. So I hope that the definition of stable matching is clear to you. And then we talked about the Gale-Shapley algorithm, which is like, if it is a man-oriented stable matching, we start with, say, you can start with from any boy, but suppose for simplicity, you start with the boy 1, and then boy 1 will be matched with the highest ranked woman in his preference list. But this is so matching. This matching is not final. This might break also at some point of time. And the algorithm was like, when there is a boy who is free, you keep on doing this thing. So at this moment, at the first iteration, the boy 1 is suppose matched with his highest preferred girl and or woman, and then we go to second man, and second man, suppose the second man's preference, first preference is also the first preference of first man. So then there is a problem that both of them, suppose man 1 and man 2, both of them prefer, say, girl, say woman 2. Then there is a problem. Then in that case, we look at woman's preference list. So we'll look at the preference list of woman 2, and we'll see whom she prefers most, and she will she may break the previous engagement if she prefers, say, if woman 2 prefers man 2 more compared to man 1. If that is the case, she will break the engagement with man 1 and she will be engaged with man 2. So this is how the Gale-Shapley algorithm works, and you just continue this process until all the mans are matched. So this is what the stable matching is, and it is explained in the lectures. I request you to revisit them. Revisit them again. And then we talked about several examples to illustrate stable matching using Gale-Shapley algorithm. Okay. There are some general questions like, what are its application of day-to-day life of graph theory? They are a very generic question, like application of graph theory. You will see the network. So, for example, we have studied the connectivity of a graph also. Like, so what is why we need a graph or a network with high connectivity? Because what is let me just talk about connectivity, because you're talking about mostly about the matching in graph. So we never talked about connectivity. So this is one example of graph theory in real life also. Like, there are in real life we talk about network, different types of network, and what we want is that we want a network with high connectivity. And what is the connectivity of a network or of a graph? There are two types of connectivity. One is vertex connectivity and other is edge connectivity. So the vertex connectivity is the minimum number of vertices that you need to remove from the graph to make the graph disconnected. What is the application of this one? So the application is, we are not really removing something from the network, but some node might fail in the network. So that's the whole thing. And then you have to keep the network in, you should design, or you should have a network in such a way that it has high connectivity, in the sense that suppose its connectivity is say 10, the network has connectivity 10, then you know that by, even if 7 nodes of the network fail, then also the graph will remain connected. So you can afford up to the afford the failure of say about 10 or 9 nodes, and still the network will remain connected. So that means you can reach from one path, from one node to another node. So similarly, talked about the edge connectivity also. The same application of the edge connectivity is that not necessarily only the node will fail, the links between two nodes might fail. So similarly, we need a network which is of high edge, which is having high edge connectivity, in the sense that if the edge connectivity is, for example, say 6, then I know that even if the 5 links or the edges are um, uh, becoming defective after some time, still the network will be, network will remain connected. So this is how one easy example of